Section 15.6. Solving a linear congruence. Now that you know how to safely manipulate congruences without losing strength, we can tackle the problem of how to solve a linear congruence AX is congruent to B mod M, where A, B and M are given constants, and X is the unknown value we are trying to find. In the special case when B equals 1, X is the multiplicative inverse of A modulo M. Most textbooks mention only one technique, called the extended Euclidean algorithm. The Euclidean algorithm is commonly attributed to Theaetetus of Athens, who lived about a century before Euclid. That is a perfectly good method. It may be the right method to use when the modulus is small, or when the modulus has several different small prime factors. It is definitely the right method when the factorization is unknown and there is a likelihood of small factors. In cryptography, however, there are only two common cases where we need to calculate the multiplicative inverse, when the modulus is a prime and when the modulus is a power of 2. This section will describe a simpler, more direct method. Section 15.6.1. Reducing a congruence. The basic method for solving a congruence AX is congruent to B mod M is to repeatedly reduce the coefficient of X. The simplest method is res M. It multiplies the congruence by an integer n that is just large enough to make the coefficient of X at least as large as the modulus. That is, a brackets n minus 1 is less than m is less than or equal to an. You can determine the value of n just by dividing m over a and rounding up, so 2.0000 stays as 2, but 2.0001 would become 3. When the coefficient is reduced modulo m, the result is a smaller coefficient. Let's begin with a simple example of res m just to get the basic idea and to make it easier to follow the discussion later when things start getting complicated. Take the congruence 38x is congruent to 55 mod 101. We know 101 divided by 38 equals 2.658, so we multiply the congruence by 3 and then reduce it modulo 101 like this. Notice that the coefficient of x was reduced from 38 to 13. This can be reduced again. We have 101 over 13 equals 7.769, so we multiply the congruence by 8 like this. We're almost there. 101 over 3 equals 33.667, so we multiply that last congruence by 34 and the coefficient of x is reduced to 1. We can check this result by plugging x equals 36 back into the original congruence. 38x is congruent to 55 mod 101. Replacing x by 36 gives 38 times 36, which is congruent to 55 mod 101, which is 1368, which is congruent to 55 mod 101, which is true. The correct answer is x is congruent to 36 mod 101. Section 15.6.2. Half and half rule. Let's look at a small improvement. We can call it the half and half rule. About half the time the fractional part of m over a is less than 1/2, and half the time it is more than 1/2. Let q equals m over a. Then half the time qa is closer to m, and half the time brackets q plus 1a is closer to m. A numeric example may help to make this clearer. Let m be 101 and let a be 40. Then q equals 101 over 40 equals 2.525. The fraction 0.525 is more than 1/2. If you take 40 times 2, the result is 80, which is 21 less than 101. If you take 40 times 3, the result is 120, which is 19 more than 101. So 40 times 3 is closer to 101 than 40 times 2. Thus, n equals 3 is the best multiplier. Suppose instead a is 41, then m over a equals 101 over 41 equals 2.463. This time the fraction 0.463 is less than 1/2. If you take 41 times 2, the result is 82, which is 19 less than 101. If you take 41 times 3, the result is 123, which is 22 more than 101. So 41 times 2 is closer to 101 than 41 times 3. Thus, n is the best multiplier. To recap, when the fractional part of q equals m over a is less than 1/2, na is closer to m if we round q down, but when the fractional part of m over a is more than 1/2, na is closer to m if we round q up. Using the floor and seal notation, section 13.3, if frac brackets q is less than 1/2, choose n equals floor of q, but if frac brackets q is greater than 1/2, choose n equals seal of q. That sounds easy enough, but there is a complication. When n equals seal of q, na is larger than m, so you reduce the congruence by subtracting multiples of m, as we did at the beginning of this section. When n equals floor of q, na is smaller than m, so you reduce the congruence by subtracting it from multiples of m. Start with, since 101 over 41 equals 2.463, multiply the congruence by 2, giving, subtract this from multiples of 101, namely, since 101 minus 82 equals 19, and 202 minus 180 is 22, you get. To illustrate how much of an improvement this makes, let's solve a congruence with and without the half and half rule, side by side. Without the half and half rule, the reduction takes 8 steps. With the half and half rule, the reduction takes 4 steps. The ratio varies for different coefficients and moduli, but 8 to 4 is reasonably typical. Res m using the half and half rule can be called res mh.